So in iron making, during my experiences, I have learned that the red line is not just a digital readout. It's a razor edge between a productive campaign and a 100-ton disaster. So we are here to talk about the anatomy of failure. By the end of this session, you'll able to diagnose the pathological pattern of the hearth corrosion, master the thermal threshold that signal and imitate breach, and implement the preventive medicine of material resistance and thermodynamic shielding. So look at the wireframe on your screen, that glowing red horizontal line slicing through the hearth represent the red line threshold we must never cross. So if we understand the physics behind that line, we can keep the best contained for 2 decades. If we don't, the furnace becomes a ticking time bomb. To prevent a breakage, we have to stop viewing it as a random accident and start seeing it as a predictable process. So, coming to the breaking is a process, not an accident. So, a modern blast furnace is designed to live for 20 years plus, but that survival requires us to act as diagnosticians rather than just operators. So, on the left, you see the healthy operation model, a calm blue shaded furnace representing a stable thermal gradient. On the right, however, is a progressive disease. See those orange fractures spreading behind the steel walls. That is the accelerated corrosion. It is not visible from the outside until the molten iron actually breaches the stave cooler. So what? Here is simple. If you are not monitoring the invisible erosion happening behind those walls, you are effectively flying blind. Once that internal disease progresses unchecked, the structural integrity of your primary asset is already compromised beyond simple repair. We must treat every thermal shift as a symptom of this progressive erosion. This disease doesn't attack randomly, it follows a very specific pathological pattern in the lower hearth. So, coming to the pathology of elephant foot corrosion. So, breakages rarely happen at random. They follow a predictable pattern we call elephant foot or garlic shaped corrosion. So, look at the central diagram. See how the circulating hot metal has hollowed out that lining, creating that characteristic bulge at the bottom. This target zone is almost always 1 to 2 meter around the middle line of the taffel. Now look closer at the magnified weakest link on the right. Notice the red arrow pointing to the exact point between two stave coolers. That precise location is where artificial cooling intensity is at its lowest. This is the operational. So what? Your lining will always fail at the point of least resistance. If your circulation is violent, it will find these cooling gaps and scour them until the steel is exposed. Since we cannot see this with our own eyes, we have to rely on our own thermal vital signs. So, monitoring the vital signs, the thermal threshold. So, because the hearth interior is invisible, we use heat flux intensity as our proxy for proximity of molten iron. Follow the gauge from the left to right. The safe zone is blue, but as we move to the center, we hit the warning zone at 35.8 kilowatt per square meter. At this point, your lining is severely eroded and intervention is mandatory. But look at the far right, the red line at 43 kilowatt per square meter. So this is the critical threshold where the heat flux hit 18,000 kilocalories per square meter hour. At this stage, the molten iron has made direct physical contact with a stave cooler surface. Once you cross this line, your cooling water can no longer lower the temperature. Catastrophic burning of the stave is now imminent. To see what happens when we ignore these threshold, so let's analyze the 1986 capital steel crisis. So, case study of the capital steel number 4 crisis on March 5, 1986. The number 4 furnace at Capital Steel provided a textbook example of thermal escalation. So 8 a.m. the water temperature difference between adjacent stave 32.1 and 32B began to separate. By 9 a.m. the delta T on the stave 32.1 climbed to 1.2 degrees Celsius. So look at the rate trajectory on the chart. The heat flow intensity didn't just rise, it skyrocketed, breaching the red line and hitting 49.5 kilowatt per square meter. So this is the so what of high speed tapping operation. So if you push the productivity too hard without respecting the local heat flux, the molten iron will invade the stave cooler completely. The red line was the breast and the countdown to a blowout began in earnest. So once that threshold is shattered, chemistry measure transition from preventive or prevention to damage control. So the blowout when intervention. So when intervention fail, when the thermal threshold is permanently broken, we can say you are no managing an evacuation. At 10:17, tapping began. At 10:26, operator shifted to the breeder for depressurization. Look at the spike on the graph at the 10:40. That's where the dispersion set in and cooling water pressure was force up to 20.5 kilogram per square centimeter. It didn't matter. At 11:20, the exterior steel shell turned glowing red. See the yellow smoke icon. That's the visual confirmation of the stave failure. At 11:55 am, the breakage occurs. Explosion rang out as the stave cooler burned through, releasing 100 tons of molten iron into the floor. So this is the ultimate operational failure, a total loss of containment. So recovering from such a failure is not a simple patch job, it's a multi-step engineering surgery. So coming to our surgical extraction and recovery. So when a breakage occur in the elephant foot zone, recovery require a precise multi-step engineering operation. So step 1, we isolate and cut. The exterior steel shell must be cut away exactly along the perimeter of the compromised steps. In this case, step 31, 32 and 33. Step 2, fragmented extraction. Bond steps fused to the surrounding material and must be cut into small pieces for removal. So step 3 involves watering down and cleaning the exposed residual brick and coke to supplement the uniform depth. So finally step 4, we construct new refractory brick or laid fresh steps are installed and the shell is welded shut. So this process is expensive, dangerous and takes week of downtime. Prevention is always cheaper than surgery. So the first step is that the prevention is selecting material that can survive the Earth's hostile environment. So preventive, coming to the slide of preventive maintenance or let us coming to the preventive medicine. One, the Material survivability matrix historical data from the capital shell shows that the preventing breakage start with the fundamental material reasons. Look at the erosion speed uh, column. So the carbon ramming may erode at rate of 1.6 millimeter per day, lasting less than 1,000 days. Camote brick is better, but look at the bottom row. High alumina brick, its erosion speed is more than 0.375 millimeter per day, a 400% reduction in erosion speed. So which is compared to the which can be compared to the our ramming mass. So by transitioning to the comprehensive high alumina brick structures, we create the foundation for multi-decade furnace lifespan. So what is clear, your choice of refractory at the build stage dictate your risk profile for the next 20 years. High alumina is not just an expense, it's an insurance policy. So beyond material, we must also engineer the liquid iron itself to act as a buffer. So coming to our preventive medicine 2, which is about a salamander. Depth optimization to minimize the circulation stress that causes elephant foot. Consider engineer a deliberate salamander depth, a pole of residual iron below the tap hole. So optimal buffer. So if the depth ratio is too shallow, less than 15%, the circulation remain violent, directly hitting the bottom lining. So if it is too deep, over 20%, you are wasting hundred of cubic meter of internal volume for negligible gain. So the sweet spot is that 15% optimal buffer. It provides a calm a reservoir of the iron that protect the hearth floor without sacrificing production capacity. We target a maximum depth of 2.5 meter. These pool act as a liquid shock absorber, dissipating the energy of the falling iron before it can erode the refractory. So this liquid buffer also enable the most powerful defenses we have. So coming to our next slide, which is about a autogenic protective crust. So the salamander depth is not just a physical buffer, it's an active thermodynamic shield. So look at the temperature on the hearth. As the hot metal drop 2.5 to 4 meter below the tap hole, its temperature naturally drop from 1460 to 1200 degrees Celsius. So at this lower temperature, carbon solubility decreases. What happens next? Beautiful engineering. So large amount of carbon physically precipitate out of the liquid iron, setting at bottom to form a durable regenerating layer of deposited carbon. This shield crust provides a natural shield for the hearth bottom. We are not just relying on the brick, we are using the chemistry of iron to grow a protective skin. However, if you lack active cooling below the crust, the heat will find its way out. So the danger of abyss is the uh, different plant incidents. So without active bottom cooling, the heat has nowhere to go but straight down uh, in September 1962. Operator noticed tapping volume inexplicably dropping by hundred of tons. So simultaneously, white smoke, which was 95.4% CO2, began erupting from crack in the concrete foundation. Over 250 ton of molten iron had quietly burned directly downward, penetrating 2.5 meter into the uncooled concrete. The escaping gas was actually the chemical byproduct of the concrete's pebble boiling and decomposing. So this is what happens when you lose control of the downward influx, the furnace literally tries to dig its way to center of the path. To prevent this digging, we use what professor called the thermodynamic force field. So coming to the next slide, which is on a preventive medicine 3. So now the Dr. Forsyth in the 1950s, Professor Axe used electrical field to prove the thermodynamic necessity of active hearth bottom cooling. On the left, an uncooled foundation create a pot-shaped thermal profile, putting heat relentlessly downward. So now look at the right, active bottom cooling by introduction cooling pipes. The isotherms are flattened. The cooling layer act as a thermodynamic force field, catching the downward heat flux and spreading it horizontally. These physically prevent the molten iron from ever having the thermal energy to dig into concrete. The so what here is structural active cooling is the only thing standing between your furnace and the concrete foundations destruction. So when we combine all these strategy, we move from emergency management to long-term stability. The blast furnace longevity framework furnace survival is not achieved by a single silver bullet. It's a multidisciplinary equation. First, the structural buffer, maintaining that 15% salamander depth and carbon precipitation crust. So second is material resistance, utilizing high alumina or high graphite carbon brick. And third is the active intervention, that is thermodynamic bottom cooling and constant thermocouple monitoring. So when you master this equation, you achieve 10 to 20% year lifespan that defines a world-class um, operation. So don't wait for the yellow smoke or a red shell. Manage your threshold, represent the red line, and you will ensure decade of stable high yield operation.